Good morning, champs. Today, we introduce one of the most powerful tools in complex analysis, the residue theorem. We start with an example. We compute the integral of e to the z divided by z times z minus 1 cube along a circle that contains both 0 and 1. First, we identify the poles. We have a simple pole at 0 and a pole of order 3 at 1. Now here is the key idea. Each pole contributes a number to the integral. These numbers are called residues, and the residue theorem says that the integral is equal to 2 pi I times the sum of all residues inside the curve. So now the question is, how do we compute these residues? There are two important formulas. First, for a simple pole. If the function looks like something divided by z minus a, then the residue is just the remaining part evaluated at a. So we remove the bad factor and plug in the point. Second, for higher powers. If the denominator has power k, then we take derivatives. Specifically, we take the k minus 1 derivative of the remaining function and divide by factorial. So higher powers mean more derivatives. Now we apply this to our example. First, the residue at 0. We rewrite the function as something divided by z. The remaining part is e to the z divided by z minus 1 cube. For a simple pole, we just plug in 0. That gives minus 1. So the first residue is minus 1. Now the residue at 1. We rewrite the function as something divided by z minus 1 cube. The remaining function is e to the z divided by z. Since the denominator has power 3, we take the second derivative, then evaluate at 1, which gives e, and divide by 2 factorial. So the residue is e over 2. Now we add both residues, minus 1 plus e over 2, and multiply by 2 pi I. So the final result is pi I times e minus 2. And this shows the full power of the residue theorem. We don't compute integrals anymore. We just compute residues and add them.